Today we'll speak about linear regression, one of the most widely used models in machine learning and statistics. Our plan is as follows. First, we will discuss our goals, what we aim to understand in terms of mathematics, programming, and visualization. Then we will look at the main types of machine learning tasks and take a closer look at the regression task. We will explore the concept of a dataset in detail, along with related terminology. We'll examine what linear models are and how to measure errors in regression tasks. Next, we'll move on to training and learn how to build linear regression models using the normal equation. Finally, we'll see how to get predictions on new data using the trained model. We should learn to easily switch between mathematical, graphic, and programmatic representations of objects. Always understand what kind of mathematical object we are dealing with, a scalar, vector, or matrix. Easily convert between matrix vector form and expanded form. Take into account the dimensions of data structures when performing operations on them. Let's start. All machine learning tasks can be divided into three groups: supervised learning, unsupervised learning, and reinforcement learning. Supervised learning means that there is a dataset with examples x sub I and corresponding responses y sub I for each example. We can also call examples as instances or samples, and we can call responses as labels or targets. We need to train a model that predicts y for any given x. The main examples of tasks in supervised learning are classification and regression. In classification, y belongs to the set containing the elements 1, 2, and so on up to c. In the regression task, y is a real number. Another task in machine learning is unsupervised learning. In unsupervised learning, the examples in the dataset do not have responses, and we need to find structure in the data. The main example of unsupervised learning task is clustering, which means dividing the dataset into groups of similar objects. In reinforcement learning, an agent learns to make decisions by interacting with an environment and receiving feedback in the form of rewards or penalties. Today we will study regression, a supervised learning task. Here are several examples of regression tasks. Predicting the loan amount that a bank can offer to a client. Forecasting air temperature based on weather data. Predicting age from a photograph or voice. Estimating delivery time based on distance, traffic, and time of day. Predicting crop yield based on weather conditions, soil type, and planting time. In any case, in a regression task, we predict a continuous variable that can take values from some range of real numbers based on one or more input variables. Here we can see the graphic representation of the prediction of the loan amount that a bank can offer to a client. We have 5 clients, the information of their income, and the amount of loan that these clients can have. For example, Alice earns $1,000 and the bank can offer a $40,000 loan, while Bob earns $2,000 and can expect up to $70,000 from the bank. Since we have only 2 variables, income and loan amount, we can represent this task on a 2-dimensional plane. The next example requires 3-dimensional space. In addition to the client's income, we also include information about their age. These 2 features determine the loan amount. For example, here we can see that Bob's income is $2,000, his age is 30, and his loan amount is $70,000. In real tasks, the quantity of features can reach tens and even hundreds, but such high-dimensional tasks are hard to depict in the same way like on this slide. Let's look at the dataset of this example with two features, income and age. We have 5 examples. You can use instances or samples as synonyms. We have 2 features, income and age. Loan amount is a target variable. Here we use the variables designations. Notations for examples are x vector sub 1 or x with an arrow sub 1, x vector sub 2, and so on. Notations for features are x sub 1 and x sub 2. Notation for target variable is y. Here we see the variables designations and their values. For example, the value of the first feature, income, for the first example, Alice, x11 is 1000, and the value of the second feature, age, for the third example, Charlie, x32 is 50. The rows of the dataset, excluding the target variable, form feature vectors or sample vectors. X vector sub 1 is a tuple. It contains the values of both features for the first example. X sub 11 is the value of the first feature for the first example, and x sub 12 is the value of the second feature for the first example. Vectors are denoted by lowercase letters with an arrow on top or by bold lowercase letters. The index of the feature vector and the first index of axis is the same, 1. The second indexes of axis are 1 and 2. These are feature indexes. The dataset is usually represented in the form of design matrix or feature matrix of size n by d. In our example, n equals 5 and d equals 2. One row of such matrix is a feature vector and has designation, for example, x vector sub 1. Each element of a vector or a matrix is a scalar, that is just a number. All values of target variable together are a target vector of size n. In our example, n equals 5. Each element of target vector is a scalar. Here is the example of Python code that defines a dataset as a design matrix and a target vector. First, we import numpy as NP. Then we define xList as a list of lists. It's our design matrix. After that, we convert it to numpy array x. So we have a design matrix x, which has 5 rows and 2 columns. Now we define ylist as a list. It's our target vector. After that, we convert it to numpy array y. So we have a target vector y, which is a one-dimensional array or vector with 5 elements. Pay attention that numbering of matrices starts with a 0 in Python and starts with 1 in mathematics. So the element x11 in design matrix is the element 0, 0 from numpy array x, and element y1 in target vector is the element with index 0 from numpy array y. One line of the matrix is a vector of one sample, and one column of the matrix is a vector of one feature. Now let's return to the regression task. We are given a design matrix X and a target vector Y, or ground truth vector. The goal is to find a function or algorithm or model A such that A of X vector sub I equals y sub I pred, which approximately equals to y sub I, where x vector sub I is the ith row of x. We can say that the input to the model is the vector x sub I, and the output is the predicted value of the target variable y sub I pred. The model should predict in such a way that y sub I pred is as close as possible to the ground truth value y sub I. One of the most commonly used types of models for solving regression problems is the linear model. Let's take a look at what that means. Suppose we have a sample x vector sub 1 equals x sub 1 1, x sub 1 2. As we've already seen, the model should take x vector sub 1 and predict y sub 1 pred. A linear model has the following form. It is the sum of all features x, each multiplied by its corresponding weight w, plus a special term called the bias or intercept. Weights and the bias are model parameters. If we know the weights and the bias, then we know everything about our linear model. The model learns its parameters during the training process. Let's look at the graphical representation of our regression task. Here we have only one feature, income, and want to predict the loan amount. As we have already seen, such a task can be represented on a two-dimensional plane. Linear models on a two-dimensional plane are represented by straight lines. Here our model is shown as a red line. The equation of this line is W0 plus W1 x1. We can find the loan amount predicted by our model by finding the value on the y-axis for any x which represents income. For example, for Alice, with an income of $1,000, the model predicts this value. Model line is close to the examples, but the data points deviate from it. For example, if we take Alice, regression line gives us the value higher than is real for Alice. Let's look at what the actual parameter values of the model might be in our case. For the model shown in the illustration, W0 is 27,225 and W1 is 19.9. How exactly these values were obtained, we will learn later when we study model training. W0 is the point where the line crosses the y-axis. In other words, it's the value of the target variable that the model will output if all features are 0. Yes, it might seem strange if the bank grants a loan of almost $30,000 to a person with 0 income, but we can set a minimum income threshold at which we apply our model. The weight W1 is equal to the tangent of the angle between the line and the x-axis. By calculating the arctangent of W1, we can determine the angle. In our case, it is 87.1 degrees. It may not be obvious from our graph that the angle between the line and the x-axis is close to 90 degrees. The reason is that the axes have different scales. Income changes in steps of 1,000, while the loan amount changes in steps of 20,000. If we use a 1-to-1 scale, it becomes clear that the angle is indeed close to 90 degrees. Let's look at the model parameters from the perspective of interpretation. As we've already seen, W sub 0 is the model output when all features x sub I are equal to 0. You can think of it as the default predicted value. W sub I is the weight coefficient that determines the influence of feature x sub I on the result. There are two important things to keep in mind. First, the sign of the weight determines the direction of change in the target variable when the feature value changes. If the weight is positive, the target variable increases as the feature increases. If the weight is negative, the target variable decreases as the feature increases. In our case, income is positively associated with the loan amount. The higher the income, the more money the bank is willing to offer. But for feature like the number of existing loans, the relationship would likely be negative. Second, the magnitude of the weight shows how fast the target variable changes when the feature value changes. The larger the absolute value of the weight, the faster the target variable changes, and vice versa. Let's see how to implement linear regression in Python. Here we define the design matrix X and target vector Y. It's the same example like on the previous slides, with 5 examples and only one feature. To build linear regression, we use one of the most well-known machine learning libraries, scikit-learn. We import linear regression class from scikit-learn.linearModel module and matplotlib.pyplot as PLT. Model is an instance of the linear regression class. The method used to train the model in scikit-learn is called fit. So we call fit method with x and y as arguments. As a result, we get the parameters of the model, including the bias or intercept and the weight for the first feature. Since array indexing in Python starts at 0, the weight for the first feature has index 0. The equation of our model is as follows. The graph with samples as blue dots and red linear regression line we got is here. The visualization of 3D example is on the slide. We have two features, x sub 1 and x sub 2. The first feature still corresponds to income, while the second feature corresponds to age. The mathematical representation of the linear regression model is shown here. For our previous example with one feature, the regression was a line, and now for the example with two features, the regression is a plane. Here we see Python code of linear regression for the 3D example. First, we define the design matrix X and target vector Y. It's the same example like on the previous slide, with 5 examples and 2 features. The code for training the linear regression remains the same as for 2D example. But now, instead of one weight, we have 2 weights, for the 0th feature and for the first feature. Thus, we have a total of 3 parameters. Here we see the equation of the regression plane. Let's now learn how to write expressions for linear regression in a compact form, so that they don't depend on the number of features, since there could be dozens or even hundreds of them. Our sample is x sub I vector equals x sub I1, x sub I2, up to x sub id. To be shorter, x sub I is a vector with components x sub I1 through x sub id. The model A of x sub I vector equals w0 plus w1 times x sub I1 plus w2 times x sub I2, and so on up to wd times x sub id. The compact notation is given on the slide. The model A of x sub I vector is a bias term w sub 0 plus a weighted sum of the products of the model weights and the features. We can make the notation even shorter by introducing the dot product of vectors, a very commonly used operation in linear algebra and machine learning. Dot product, which is also called scalar product or inner product, is the sum of the products of the corresponding components of two vectors. If we represent not only the sample, but also the set of weights as vectors, then the model's expression can be written using the dot product. But the bias is still handled separately. Is there a way to include it into the dot product? If we prepend a 1 to the vector x sub I, then W0 can be incorporated into the vector W, and the model expression can be simplified like shown here. This way, we have reduced the linear regression model to the dot product of two vectors, the feature vector and the parameter vector. Since we prepend a 1 to each vector, the feature matrix gains an additional column of 1s, like shown here. The first column is the column of 1s. The second column contains the values of the first feature for all 5 examples, and the third column contains the values of the second feature for all 5 examples. Let's take a look at how to work with dot product and how to add a 1 to the feature vector in Python. First, we define the design matrix X and target vector Y. It's the same example like on the previous slide, with 5 examples and 2 features. Here's the vector of the first sample. Just a reminder, in Python, indexing starts at 0. We set the parameters manually. If we try to compute the dot product of the sample vector and the parameter vector, we will get an error because their dimensions don't match. Now we first concatenate 1 with our sample. And when we try again to get the dot product, everything is all right. Remember that one of the names for the dot product is scalar product, because the result is always a single number, a scalar. Now let's add a column of 1s to the entire design matrix. We tell NumPy to display numbers in fixed point notation instead of scientific notation. Let's create the column of 1s. Technically, it's a matrix with a single column. It has the same size as the number of samples. In our example, 5. Then we concatenate it with our design matrix. After that, we can calculate the dot product of any example and the parameter vector, with no errors. Now let's try to answer the question how to measure the error in regression task. We use our example from the previous slides. It has 5 examples, 2 features, and 1 target variable. Let's say our regression model returned the following predictions. It seems that the most natural way to compute the model's error on this dataset is to find the differences between the predicted values and the target variable, and then sum or average them. These differences are called residuals. But when we sum the residuals, the result turns out to be 0. Positive and negative errors compensate for each other. Of course, this method isn't suitable for calculating the model's error. It's clear that the predictions don't exactly match the target values, so the error shouldn't be 0. We could average the absolute values of the residuals, and indeed this method for calculating error exists. It is called mean absolute error. However, a more common approach is to compute the squares of the residuals. In this case, we square each residual and then average them. Error is not 0 now. This method of calculating error is called mean squared error, or MSE. Let's look at the mathematical notation. MSE of model A on dataset X equals 1 over n multiplied by the sum as I goes from 1 to n of the squared differences between yi and yi pred. In other words, MSE of model A on dataset X is the average of sum over all n observations of squared differences between the true value and predicted value. In this formula, we can replace yi pred with the output of the model A evaluated on the sample vector xi. MSE is an example of a loss function. A loss function or cost function is a mathematical function that measures the discrepancy between a model's predictions, y pred, and the true target values, y. Let's look at the graphical interpretation of error calculating. We have the example with one feature, income. Here is the residual, the difference between the true and predicted values. If we square such residuals for all the samples and find the mean value of such squares, it will be the MSE, mean squared error. In matrix vector form, the mean squared error is written as follows. MSE of model A on dataset X equals 1 divided by n times the squared norm of the vector y minus the design matrix X times the parameter vector W. Let's break down this formula. This part represents a norm of the vector y minus the matrix X times the vector W. The norm of a vector is denoted by double vertical bars and represents the length or magnitude of the vector. It is calculated as the square root of the sum of the squares of the vector components. To understand what a vector norm is and how it is calculated, we can look at this illustration. Here, to find the length of the vector, we apply the Pythagorean theorem. The square of the hypotenuse, that is the length of the vector, is equal to the sum of the squares of the legs, that is the components of the vector. The norm of the vector z, which equals 4, 3, equals the square root of 4 squared plus 3 squared, which equals the square root of 25, which equals 5. So the norm of the vector, or its length, is 5. Now let's figure out which vector's norm we are calculating. The red part in this formula is the matrix vector product of matrix X and the vector W. Let's remind what is the matrix vector product. Let's assume that the matrix X has 5 rows and 3 columns. Don't forget the added column of ones. And the vector W has 3 values. The vector W can be viewed as a matrix with a single column. The main rule of matrix multiplication is that a row of the first matrix is multiplied by a column of the second matrix. This means that to get the first element of the resulting vector, we multiply the first row of matrix X by the vector W. To get the second element, we need to multiply the second row of the matrix by the vector. Note that the elements of the resulting matrix are the dot products of the sample vectors from matrix X and the parameter vector W. From the rule a row is multiplied by a column, it follows that the inner dimensions of the matrices must match, and the dimensions of the resulting matrix are equal to the outer dimensions of the original matrices. Now let's recall that the dot product of a sample vector and the parameter vector is the prediction made by the linear regression model. Therefore, the product of matrix X and vector W gives the vector of model predictions y pred. Let's now show, using our example, how the model predictions are obtained through the matrix vector multiplication. Let's take the matrix for our dataset with two features and the parameters that we obtained earlier after training the linear regression model. By multiplying a row by a column, we get the dot products of the sample vector and the parameter vector, which represents the model's predictions for the first example, second example, and so on. Let's return to the MSE expression in matrix vector form. We understood that the product of x and w is the prediction vector. Now subtract the prediction vector from the target vector. Here we expanded this difference and obtained the resulting vector, which contains the differences between the target values and the predicted values. Next, we can find the norm of this vector by squaring its components and then taking the square root. However, notice that in the MSE expression, the norm is squared, which means the square root cancels out. Let's substitute the expression we obtained back into the original formula and see what happens with the MSE in the end. When we substitute the squared norm of the vector into the MSE expression and write it in a compact form, we will see that it matches the familiar formula for MSE in its standard non-matrix vector form. So we have learned to express MSE both as the mean of squared residuals and in matrix vector notation. Let's now see how to calculate MSE in Python. As usual, first let's define the design matrix and the target vector. We use linear regression class from scikit-learn as earlier and get the parameters of the model. Let's define our function for calculating MSE. Python lets us define this function very close to the mathematical expression, thanks to its ability to perform matrix vector operations. So it's just the mean squared value between the true values and the predicted values. Of course, scikit-learn has a built-in function for calculating MSE. We will compare the results of our function and the one from scikit-learn. First, we get the prediction vector from our trained model. Then we calculate MSE, first using our own function and then using the built-in function. As you can see, the results are the same, so we defined our function correctly. It's time to speak about training. In the case of linear regression, model training involves finding the parameter vector w that minimizes the model's error, or in other words, loss function. This can be MSE, for example. The optimization problem is formulated as follows. We need to find a parameter vector w that minimizes the MSE error. Or in matrix vector form, it can be written so. To find the minimum of the loss function, it is necessary to compute its gradient, the vector of partial derivatives, and set it to 0. The gradient of the MSE is written as follows. The inverted triangle symbol is called the nabla operator. According to the rules of matrix calculus, which we won't go into detail about here, the gradient of the MSE is expressed as follows. To find the vector w that minimizes the MSE, we need to set the gradient of the loss function to 0 and solve the resulting equation for w. Let's first expand the brackets. Then move the first term to the right-hand side and divide both sides of the equation by the matrix x transpose multiplied by matrix x. The analog of dividing by a matrix is multiplying by the inverse matrix. After that, the left-hand side of the equation will contain only the vector w, meaning we have obtained an expression for the optimal parameter vector at which the MSE reaches its minimum. There is no other vector w for which the MSE would be smaller. This expression is called the normal equation. Actually, this is a rather rare situation in machine learning when we can obtain the optimal model parameter vector using a fairly simple equation in a single step. Usually, finding the parameter vector requires a gradual multi-step approximation to the optimum using an algorithm called gradient descent. Let's analyze the components of the normal equation. X is a design matrix, a matrix where each row represents a data sample and each column represents a feature, including a column of ones. X superscript T is the transpose of matrix X, where rows become columns and vice versa. We need to multiply the matrix X transpose by the matrix X, and then find the inverse of the resulting matrix. Then it is necessary to multiply the inverse matrix by the transpose of X and multiply the result by the target vector Y, containing the true output values. As a result, we should obtain the optimal parameter vector W. Let's look at an example of how the normal equation works. Let's take a simple dataset consisting of 3 examples, 1 feature, and a target variable y. We need to build a linear regression model using the normal equation. The dataset is represented on the plane by 3 points, 2, 1, 3, 3, and 5, 4. You can see the samples on the graph. X-axis represents the value of features and y-axis the true values. Let's rewrite the normal equation so that we have it clearly in front of us. The dataset is represented as the design matrix X and the target vector Y. Pay attention that we added the column of ones. First, we do the matrix multiplication of X transpose and X. X transpose is the matrix X rotated by 90 degrees. Let's verify that the inner dimensions of the matrices match. Recall that the dimension of the resulting matrix corresponds to the outer dimensions. We have row times column rule, where the elements of a row in the first matrix are multiplied by the corresponding elements of a column in the second matrix, and the results are summed to produce an entry in the resulting matrix. For example, to get the element in the first row and in the first column, we take the first row of the first matrix and the first column of the second matrix. 1 times 1 plus 1 times 1 plus 1 times 1 equals 3. To get the element in the first row and in the second column, we take the first row of the first matrix and the second column in the second matrix. 1 times 2 plus 1 times 3 plus 1 times 5 equals 10. And so on. So we get matrix of size 2 by 2. The next step is finding the inverse of the matrix. The inverse of the matrix is the following. We won't go into the rules for finding an inverse matrix right now. They can be found in any linear algebra textbook. But we will check a key property of the inverse matrix. When a matrix is multiplied by its inverse, the result should be the identity matrix, which has ones on the main diagonal. Indeed, we can see that the inverse matrix has been found correctly. The next step is multiplying the inverse matrix by the transpose matrix. We get matrix of size 2 by 3. And now it's time to multiply this matrix by the target vector to obtain the solution. When multiplying a 2 by 3 matrix by a 3 by 1 vector, we obtain a 2 by 1 vector. This is the vector of optimal parameters. It consists of two elements, W0, which is the bias, and W1, the weight. Now, when we have the parameters of the model, we can make an equation for our regression model. Let's plot the regression line on the graph. It's a red line here. We can see that the line passes fairly close to the blue points, but there is still some non-zero error. However, in terms of MSE, this is the best possible line we can draw. For any other line, the MSE would be higher. Now let's take a look at how the normal equation can be implemented in Python. We use the same dataset as on the previous slides, 3 samples with 1 feature. We make the column of ones. We concatenate it with our design matrix. Here we define the target vector. First, we transpose the matrix X. The columns become rows and vice versa. We calculate the multiplication of the transposed matrix and design matrix. Next, we calculate the inversion of the previous matrix. And then we get the multiplication of it with the transposed matrix. Then we need the multiplication of the last matrix with target vector y. The result is the optimal parameter vector. When we have the model parameters, we can write down the linear regression model. It's time to speak about getting predictions. To obtain predictions for the entire dataset, we should multiply the design matrix by the parameter vector. We get 3 values, which are the dot products of the sample vectors and the parameter vector. As you can see, these predicted values are situated on the regression line at the points corresponding to the feature values. For example, for the first sample, at point 2, true value is 1, while the predicted value is the value on the regression line at point 2. Now we'll calculate the MSE for this example. Let's recall that the MSE is the squared norm of the difference between the target vector and the prediction vector, divided by n. First, let's compute the difference between two vectors. Here n equals 3 because the dataset contains 3 examples. The squared norm of the vector is the sum of the squares of its individual components. As a result, for our linear regression model, the MSE equals 0.2143. We cannot achieve a lower MSE than this value with a linear model. Here we see Python code of computing MSE. We set up the dataset, train the model using the linear regression class from scikit-learn, make predictions, and calculate the MSE using the built-in function as well. The result is the same as on the previous slide when we made all the steps manually. The only small difference is in the third prediction due to rounding errors. Today we explored the regression task, learned how to denote datasets, understood how linear regression models work, got to know how to calculate model errors, and saw how to train a linear regression model using the normal equation. All of this by using mathematics, programming, and visualization at the same time.